Hello everyone, I'm Qinying from Zhejiang University. Today I'm going to introduce our project, SysTrust. This is a joint work with students and professors at Zhejiang University, EPFL, UCLA, and Georgia Tech. SysTrust is the first fuzzing framework for IoT trusted operating system, and it has identified 70 previously unknown vulnerabilities. Nowadays, trusted execution environments are essential to IoT security. They protect numbers of IoT devices, such as smart lock and fiddle security key. So, what is the definition of a TEE? A TEE is an isolated and trusted environment shielded against local attacks. It introduced the concept of a secure world and a normal world. Untrusted client applications and rich operating systems are running in the normal world. Trusted applications and trusted operating systems are running in the secure world. They store, process, and protect sensitive data, such as fingerprints. In the TE architecture, trusted operating system is the primary component. It provides cryptographic operation APIs for trusted applications to implement their own functionalities. However, if there are vulnerabilities in the trusted operating system, the attacker exploits these vulnerabilities to attack other trust applications or even the whole system. It results in full control of the system, data leakage, and system-wide crashes. Previous work has found several bugs targeting trusted operating systems on mobile phones, and one of the attacks successfully extracted the 4-disk encryption keys of the Android key master services. Despite several studies on Android trusted operating system, our understanding of the security in IoT trusted operating system is still limited. Recent works use fuzzing to automate the TE testing. However, fuzzing on IoT devices are extremely difficult. Unlike trusted operating system for Android devices, IoT trusted operating systems are more hardware dependent and resource limited, which brings new challenges. First, most IoT trusted operating systems are closed source and often encrypted, which makes it hard to instrument and monitor the code execution in the secure world. In addition, IoT devices are severely resource limited, and even the minimal fuzzer cannot be loaded to the microcontroller. Second, IoT trusted operating system needs to maintain at least 20 states to implement the sensitive operations. It stores and controls the execution context into complex data structures. Without awareness of the internal state, coverage-based fuzzer cannot explore further states and will miss some bugs. To address the first challenge, we found ARM core set embedded trace microcell provides real-time instruction tracing. We can utilize a debug probe to stream the ATM tracing packets to the computer. In addition, based on the raw ATM packets, we propose an optimization for basic block to calculate the branch coverage in a lightweight way. With such a hardware-in-the-loop design, we can decouple execution to offload heavyweight tasks to our computer, including the coverage calculation and the seed scheduling. Regarding the second challenge, we observe that several variables in handler structure determine and stores trusted operating system's state. For example, after TE allocate operation, the operation state in TE operation handler indicates that one of the crypto operation is initialized. Only then the crypto operation like TE saver update can be triggered. From the observation, we can utilize the values of these variables to present a state. Similarly, we can stream the state variable values via debug plot to our computer and calculate the state coverage based on the variable values. Based on the above insights, we propose systrust, which includes two modules, the fuzzing engine and the execution engine. In the fuzzing engine, the manager generates and sends trusted operating system API sequences to the execution engine via debug plot. Then, in the execution engine, our implemented proxy client applications and trusted application will execute these API sequences to test the trusted operating system. In the meanwhile, our hardware controller collect and send the code and state coverage to the manager to get the test case generation. Next, I will explain how we obtain code and state coverage utilizing the debug prop and how this metric guide our fuzzer. Regarding the code coverage, there are two gaps we need to fix. First, the ATM component records the noisy instruction traces generated by client application, rich operating system, and the trusted operating system, which we are not interested at. To solve it, we designed an event-based filter via data watchpoint to filter noisy packets. By setting two data watchpoints, we collected ATM packets only when trusted operating system executes a system call. Second, to get basic block coverage, we need to align decoded ATM packets to disassembled instruction sequences of the firmware, which is hard and time-consuming. To solve it, instead of decoding the ATM packets, we calculate the branch coverage directly on the ATM packets. Regarding the state coverage, we need to infer the state variables in the handler struct. To this end, we send trusted operating system API sequences to the trusted operating system and record the buffers of these handler structures. Then we apply heuristics to detect the address ranges of state variables in the recorded buffers. The state variables should satisfy the following condition. First, the state variables is not randomly changeable. Second, the state variables will have different values according to different operation configurations. After getting the address ranges of the state variables, we can utilize a monitor to check the values of these state variables during the fuzzing and calculate the state coverage based on these values. With code and state coverage collected, Systrust performs seed preservation and seed selection. In the seed preservation, Systrust preserves the test cases that trigger new codes or new states. To this end, we design two maps to store the seeds as the seed coppers. The first map is a heat map, which stores the numbers of times each state is hit. The second map is a seed map, which stores the seed buckets that reach each state. In seed selection, Systrust will first search the heat map and more likely to choose a state that is rarely hit. Then, Systrust searches the seed buckets mapping to the chosen state. It will more likely to choose a seed that achieves higher branch coverage in the seed buckets. So, that's all about our methodology. In our evaluation, we evaluate Systrust against Syscaller on mTower from Samsung. The results show that Systrust outperforms Syscaller in terms of code coverage, state coverage, and detected vulnerabilities. We apply Systrust to test real-world trusted operating systems, including mTower from Samsung, LinkTEE Air from Alibaba Cloud, TinyTEE from Xinlink Cloud. Systrust discovered 70 unknown vulnerabilities, including buffer overflow, non-pointer dereference, and we got 19 CVEs so far, each rated as high severity vulnerabilities. Finally, we evaluate the overhead of Systrust subprocesses. Results show that test case execution takes the most time. Our orchestration and analysis take only roughly 1% of the overall time. At last, this is the summary of our work. We proposed the first fuzzing framework for IoT trusted operating systems, and our work has real-world impact. We detected 70 previously unknown bugs and got 19 CVEs. If you're interested in this work, please scan the QR codes. We have released all the codes and you can try Systrust by yourself. That's all. Thank you.